We're asked in this question to prove the formula for the summation of a geometric series as shown. Well, the first term is a, and then the common ratio is r, which means each successive term we're just timesing by an extra r. Okay, just keep going. I'll just write the first three down. And the last one is ar to the n minus 1, because there's always one less r than the term number, because the first term was a, it wasn't ar. So that means the second term, ar to the 1, the nth term is ar to the n minus 1. This is worth just knowing, by the way, for the nth term, but I've explained where it's come from, I hope. I don't want to call it a trick, but what the method is then involves is to times this summation through by rsn, because it basically shifts every term slightly. So a times by r becomes ar times by r becomes ar squared, and somewhere down the line, ar to the n minus 2 times by r becomes ar to the n minus 1, and then we get an extra ar to the n when I times this last one. And now we subtract them. Sn minus rsn. These are going to all cancel, and I'll just be left with a minus ar to the n. And suddenly this like long summation just turns into these four terms. I can factorize out the Sn, so Sn 1 minus r is equal to a 1 minus r to the n, and that means Sn is a 1 minus r to the n over 1 minus r. If you subtracted the other way around, you would have got a r to the n minus 1 over r minus 1, a perfectly good formula, but it's not how it's asked us to write it. So we just then have to times the top by minus 1, swaps these two around essentially, and the bottom by minus 1 equivalent fractions, and then we would get again to this formula. Okay, so just one to practice and learn. It can come up now and then, and it's also pretty interesting that we can use this argument to obtain this relatively simple formula for a geometric series. In part B, it's given that S10 is 4 times S5, and we're asked to find the exact value of R. So S10 is going to be A 1 minus R to the 10 over 1 minus R, and we're told that is 4 lots of Sn, which is A 1 minus R to the 5 over 1 minus R. Now we're told that r is not equal to 1, which means I can just times through by 1 minus r. I can get rid of these two. We're also told that a is non-zero, so I can just cancel this out as well. That's much better. So then 1 minus r to the 10 is going to equal 4 minus 4 r to the 5. We've got an equation in terms of r. Now the power is double over here. This is going to be a hidden quadratic. R to the 10 minus 4r to the 5 plus 3 is equal to 0. You can do a substitution, u equals r to the 5, or you can just factorize with r to the 5. With the substitution, you can then use the quadratic formula if you want, but it does actually factorize nicely, so that's what I'm going to do. We get a minus 1 and a minus 3, and everything checks out. So r to the 5 is equal to 1 or 3. If we take the fifth root, r is then going to be the fifth root of 1, which is just 1, or the fifth root of 3, which I'll just leave exact. We are asked for the exact value. We've already made the assumption that r is not equal to 1. In fact, we were, of course, told it earlier on. So I'm just going to reject that solution. Although it solves the hidden quadratic, it doesn't solve the original summation. Therefore, our final answer is that r is going to be the fifth root of 3.